All right, let's dive right into this explainer. Today, we are going to treat the atom like a locked, microscopic box. For centuries, brilliant scientists slowly cracked this box open, layer by layer, really trying to reveal the universe's ultimate source code.
Here is our roadmap for this journey. First, we'll meet the subatomic particles. Then, we'll look at the evolving models of the atom, how we arrange electrons in orbits, and dive into valency. Finally, we'll wrap up by identifying the atom and breaking down isotopes and isobars.
So, Section 1. Meet the subatomic particles. First up, we've got to introduce the three main characters that prove John Dalton's long-held theory of an indivisible atom completely wrong. We have the electron, which is this tiny particle with a negative charge and, honestly, negligible mass, discovered by J.J. Thomson. Then there's the proton, rocking a positive charge and weighing roughly 1,840 times the mass of an electron, thanks to E. Goldstein and Ernest Rutherford. And finally, James Chadwick rounds out our trio with the neutron, a totally neutral particle weighing just about the same as a proton.
Moving on to Section 2, the evolving models of the atom, and how this whole thing actually looked.
So, scientists took these newly discovered particles and tried to guess what the crime scene inside the atom actually looked like. They had the puzzle pieces, right, but no picture on the front of the box. We can trace this detective arc chronologically, starting from Thomson in 1904 to Rutherford in 1911, and then Bohr in 1913. And what's really cool is watching how each scientist overcame the specific physical flaws of the model that came just before them.
Let's start with Thomson. He basically pictured the atom like a watermelon. The red, edible fruit represents this giant sphere of positive charge, and the seeds scattered throughout are those negative electrons he discovered. It was actually a pretty great first attempt, because it successfully explained electrical neutrality. The positives and negatives canceling each other out. But as we're going to see, it failed pretty miserably when subjected to later physical tests.
Enter Ernest Rutherford. He decided to fire fast-moving, positively charged alpha particles at an incredibly thin sheet of gold foil. Now, based on Thomson's watermelon model, the particles should have just punched right through, no problem. And well, most did, which proved atoms are mostly empty space. But get this, a shocking 1 in 12,000 alpha particles rebounded completely back. Rutherford famously said it was literally like firing a 15-inch naval shell at a piece of tissue paper and having it bounce back and hit you. Just mind-blowing. That wild rebound meant all the positive charge and mass of an atom is concentrated in a tiny, incredibly dense center. So, Rutherford definitively found the nucleus. But he's a bit of a flawed hero in our story. You see, he proposed that electrons revolved around this nucleus in circular paths. The problem with that? Well, according to electromagnetic theory, accelerating charged particles radiate energy. So, if his model was entirely correct, electrons would constantly lose energy, spiral into the nucleus, and matter would just entirely collapse in on itself. All right, Section 3. Arranging electrons in orbits.
In 1913, Niels Bohr stepped in to solve Rutherford's stability mystery, proving that electrons actually sit in specific, non-radiating energy levels. This shifts us from the history of the atom straight into its mechanics. We're looking at electronic configuration, which is essentially the designated seating chart for electrons inside those specific stationary orbits.
So the crucial point here is the Bohr-Bury scheme. This is the strict mathematical rulebook dictating exactly how many electrons can fit into the atomic shells, designated as K, L, M, and N. First, you use the formula 2n squared, where n is the shell number. So the innermost K shell fits 2, the L shell fits 8, and so on. Second, you must fill them stepwise from the inside out. And third, there is the unbreakable octet rule. An outermost shell is strictly capped at exactly 8 electrons, no exceptions.
Let's see how this actually builds a real atom step by step. Take sodium, which has 11 electrons. Following our rules, we drop 2 electrons into the inner K shell. That leaves 9. Next, we drop 8 into the next layer, the L shell. That leaves 1 single electron, which goes all by itself into the M shell. This gives sodium a configuration perfectly adhering to the 2-8-1 distribution rule. That brings us to Section 4, valency, the combining capacity.
Once all those inner electrons are comfortably seated, we have to focus intensely on the outermost shell, because that shell dictates how the atom interacts with the rest of the universe. This brings us to valency. You can think of valency as the driving desire of an atom. Every atom wants to feel stable, and stability means having 8 outer electrons, that octet rule we literally just talked about. Valency represents the chemical lengths an atom will go to, how many electrons it will shed, steal, or share in order to reach that perfect stable state of 8.
And calculating this is just beautifully logical. You basically just count the electrons in the outermost shell. If that number is small, like 1, 2, 3, or 4, the atom will just lose or share those, so the valency equals that number. But if it has 5, 6, or 7, it's way easier to just steal a few to get to 8, so you subtract the number from 8. And if an atom already has a full outer shell, like helium or neon, its valency is a big fat 0. Those are the noble gases. They are completely stable and utterly unreactive.
Okay, Section 5, identifying the atom and its atomic identity.
Let's leave those outer electrons for a moment and zoom right back into the very center of the atom. Remember Rutherford's dense nucleus? Well, the protons and neutrons live so incredibly closely together in that tiny central volume that physicists just group them together under one family name. They call them nucleons.
And those nucleons give us our primary ID cards for the atom. The atomic number, which is represented by the letter Z, is simply your proton count. It literally dictates what element you're looking at. Then you have the mass number, represented by A, which is the combined heavy weight of all those nucleons. The protons plus the neutrons. And since electrons weigh basically nothing, that mass number is essentially the entire weight of the atom.
Finally, Section 6, isotopes and isobars, edge cases explained. To wrap up our understanding of the atomic rulebook, we have to look at some really fascinating edge cases where nature seems to playfully bend its own definitions. On the left, we have isotopes. These are basically chemical twins. They are the exact same element with the same number of protons, like carbon-12 and carbon-14, but they have a different number of neutrons, making one heavier than the other. On the right, we have isobars. Now these are completely different elements, like calcium and argon, with totally different proton counts, but by sheer coincidence, their total number of protons and neutrons adds up to the exact same mass on the scale.
Why this matters is that these aren't just abstract textbook concepts for us to memorize. We literally use the unique physical properties of isotopes to shape our modern world. Because isotopes have identical chemical properties but different physical properties, we can harness them. For instance, we use uranium-235 to fuel massive nuclear reactors. We use cobalt-60 to target and treat cancer cells, and iodine-131 to treat thyroid conditions like goiter. This microscopic structure directly saves lives. I want to leave you with this thought to ponder. We mentioned earlier that ordinary hydrogen, the most abundant element in the cosmos, is the only atom in existence that lacks a neutron. Given how impossibly precise this microscopic rulebook is, and how carefully every subatomic particle balances the others, what would happen if the fundamental structure of the universe's most common building blocks suddenly changed? It's a real testament to the delicate, perfect architecture of the atom. Thanks for joining me on this explainer, and keep questioning the world around you.